Hello again, my name is Tom Irvine, and I'm the instructor for this series of shock and vibration webinar units. And I thank Dr. Curtis Larson and the NASA Engineering and Safety Center, NESC, for making this series of webinars possible. And today we're talking about fatigue comparison methods to compare sine and random environments. And we've been discussing rainflow fatigue methods the last couple of webinar units, and we're going to continue today and in several other future units to talk about rainflow cycle, fatigue counting, and Miner's rule. And one of the powerful uses of this tool is to compare different environments. There could be a sine and random environments, or there could be two different random vibration environments, whatever. But today we'll do sine and random. So here's a power spectral density, and this is one we've seen before. It's the NAVNET P9492 level. So we have a PSD in G squared per hertz, which is really GRMS squared per hertz, versus frequency in hertz. And if we take the square root of the area under the curve, that comes out to be 6.0 GRMS. And one of the things we've done in past units, and we're going to also do it again today, is kind of a review exercise, is we're going to apply this PSD as a base input to the spring mass system. And then we're going to calculate the acceleration response, the absolute acceleration response of that mass. And we have two ways of doing it. We could do that in the frequency domain, or we could do it in the time domain. And we're going to go ahead and do the time domain method today, even though it takes us some extra steps. So our input, our base input again, is the NAVNET PSD level for 60 seconds. And we're going to assume that we have a single degree of freedom system, a spring mass system as shown here, with a natural frequency of 300 hertz and a Q value equal to 10. So that's the amplification factor, and that's equivalent to 5% damping. Now what we want to do is, well, this is going to take several steps. First we're going to synthesize a time history to satisfy that PSD. Then we're going to apply that as a base input to the spring mass system and calculate the acceleration response of the mass. Then at that point we're going to calculate the equivalent relative damage. And to do that we need a fatigue exponent. And we're going to take the value from Steinberg's text for electronic equipment and assume that that exponent is 6.4. So we're going to go through those steps with the intermediate goal of calculating the damage that this spring mass system will have in response to this PSD. Once we've calculated that damage value, then we're going to come up with an equivalent sinusoidal input, a pure sine tone at the fundamental frequency that would cause this system to have the same amount of damage as it would if it were exposed to this NAVNET PSD. So I've thrown out quite a few things at you, but as we go along in the exercise, it'll become clear what this is all about. So let's go to our MATLAB GUI package, our vibration data MATLAB GUI package. And the first part of this will just be a review exercise, but we're going to add some things to it. So this week we're up to version 6.6 and rising. So let's import some data to MATLAB. As you should recall, we have the NAVNET PSD specification as a library function. So let's just go ahead and read that in. So that's going to have two columns, frequency in hertz and acceleration G squared per hertz. And inside the MATLAB workspace, that will be called NAVNET_spec. So now that's, in fact, if I move this over, you can see we have NAVNET_spec in our workspace. Okay, so what should we do next? So let's return out of that, and let's go to, we're going to enter in a PSD, which is that NAVNET level, and we're going to do a time history synthesis from white noise. So let's begin that. So we've run this one several times before. This script synthesizes an acceleration time history to satisfy a PSD beginning with white noise. So within MATLAB already we have NAVNET_spec, and we're going to have the English units. 60-second duration. And let's view the processing options. And today we're going to take row 8. And row 8 will give us a delta F of 2.1 hertz with 256 statistical degrees of freedom. So that looks like a good way to go. So let's go ahead and calculate the time history. In other words, we're going to synthesize the time history. I should probably rename that button to synthesize, but you get the idea. And we see a whole bunch of plots come up, as we've seen before. And this one here, figure 6, this shows us the resulting power spectral density. Now when I say resulting, I'm referring to the blue line, and that's the PSD of our synthesis. And the red line is our nominal specification. So our synthesis agrees with the nominal spec well within the plus and minus 1 dB tolerance bands. And by the way, I should have mentioned this is a power spectral density plot. So we have g² per hertz versus frequency in hertz. So that's all looking well and good. Then we can check a few more plots. Here's the histogram of the synthesized acceleration time history. So we get a nice bell-shaped curve. We have counts along the y-axis. Then along the x-axis we have the binned acceleration. And this is the histogram of the instantaneous values. We have the displacement time history. Let's just note that it oscillates about the zero baseline. We have the velocity time history. Also note it oscillates about the zero baseline. And then here's probably the most important. It is the most important plot of all. This is acceleration in g's versus time in seconds. This is our synthesized acceleration time history. Overall level 6.06 GRMS. And that has a bell-shaped curve histogram as we previously seen. So this is the one that we're going to go with here. So let's go ahead and save that. We're going to save that as Excel_input, I guess. Please do this as a homework exercise, and you can name this anything you want just so you remember what it is that you called it. So let's save that. Now once we save it, this other button becomes active. And this is a single degree of freedom response to base inputs for a time domain calculation. So let's click on this, and this is one we've run before. This script calculates the response of a single degree of freedom system to base excitation. The input data must have two columns, time in seconds, and then the base acceleration. And preloaded into MATLAB, we have our synthesized time history. Excel_input. Let's go with English units here. And let's go with natural frequency of 300 hertz. And let's go ahead and calculate what our single degree of freedom system response will be. So again, a couple of plots come up. Calculation goes very quickly. Oh, by the way, this calculation, let's just have a little review here. This was essentially a modal transient calculation, although there's only one mode since it's a single degree of freedom system. And we use the David O. Smallwood ramp invariant digital recursive filtering relationship. And that was the same algorithm we used when we did our shock response spectrum calculation. Okay, here's the one we want to focus in on. This is the acceleration response for our 300 hertz system. Q is equal to 10. So we've got acceleration g versus time in seconds. And then we have the base input acceleration. Well, that's just the synthesized time history that we saw before. Now, what's the characteristics of this single degree of freedom response? If we zoom in a couple of times here, we can see that the frequency is fairly sinusoidal. In fact, if you counted the number of peaks over a certain duration and then divided by that duration in seconds, that should come up to be pretty close to 300 hertz. So the frequency is fairly sinusoidal, but this envelope is varying randomly with time. So we call this a narrowband random response. A couple other things about this. Let's go over here, and this is just some quick look statistics here. The RMS value is about 13.7 GRMS. Now, the mean value you can see is approximately 0. In fact, if we go back to the, okay, where is it? So one of these things will say Reset View. Where'd it go? Reset View. It's under Tools. The mean value is essentially 0. That means that the standard deviation and the RMS value are the same. I'll show you the formula shortly, but we've covered it before. So sometimes we kind of get a little bit lazy and we'll kind of use 1 sigma standard deviation and RMS values interchangeably. But anyways, if we take the peak absolute value and divide by the RMS, it comes out to be a crest factor of 4.57. So in other words, the highest peak for our response is 4.57 times the 1 sigma value. Now here's something that, I've said this a dozen times already. People assume in many cases that 3 sigma is the worst case response, and then they'll use that for a fatigue analysis. Well, really that's just not true, or seldom if ever is it true, because for normal distribution, random vibration, of course it depends on the duration and the natural frequency for the case of a single degree of freedom system, but it is very common to get peaks that are 4 sigma or even up to 5 sigma. So just keep that in mind. That's something I'm very particular about. Well, let's go ahead and save this acceleration response, and I'm just going to call it Excel_RASP. That'll work. Save it to MATLAB Workspace, or export it if you like. Now, when we do that, we have some shortcut buttons here, so we don't have to go back to the main dialog. Let's go ahead and look at the descriptive statistics, which will give us some of the same information that's in this box, but it will give us an expanded version. So we've run this before. It's vibration data underscore statistics. So this one will allow us to plot up some histograms and all that good stuff. Okay, so we'll talk about that one later. That one we're going to skip. Here is the histogram of the instantaneous values, the instantaneous response acceleration values. So we have counts versus G. So for our narrowband process with a fairly sinusoidal frequency, but an amplitude envelope that tends to vary randomly, we do get a bell curve histogram, or you could call that a normal distribution or Gaussian distribution if you like. Then if we just take the local peaks, the absolute peaks, and plot a histogram of absolute peaks, we get counts versus G, and this shape, we call this a Rayleigh distribution shape. So this is a histogram of the absolute peak values, so take both the positive and negative values, wherever the slope of the curve has a polarity shift or change, and that gives a Rayleigh distribution. Okay, so here's our, okay, we've already seen this time history. That's just a response time history. So some of the statistics you've seen before. You can see the mean value is essentially 0. Standard deviation, RMS, equal to one another out to the second decimal point. Skewness, approximately 0. We're going to talk about skewness and kurtosis. We've already talked about them a little bit already, but in an upcoming unit I want to revisit those parameters. But for a well-behaved random time history with a normal distribution, we expect a kurtosis equal to about 3. And then you can see the max and min and the crest factor there. And then Rice's characteristic frequency is approximately equal to the natural frequency, so it's approximately 300 hertz there. And let's see, what do we want to do next? This was just a little kind of a little side trip so we could see those histograms. And maybe what I had ought to do is just go back to this function here and have it maybe put a button here for display the histogram. Put that on my to-do list. Okay, now, but as long as we're back here, and in fact this is where we need to go next, we're going to do a rainflow fatigue. But maybe before I show you that rainflow fatigue, I think we ought to go back to the slides here for a moment or two. So let's see, what do we have on the slides? So we had our NAVNET base input PSD. We synthesized a time history, acceleration time history. Now, as I usually mention, this is the slide version, and the one I just did, that I just demonstrated, may be slightly different just due to random number seed generation, and planetary alignment and all those things. But the key statistical parameters are all the same. So this was the synthesized time history histogram for the base input, Gaussian bell curve. And then we saw the power spectral density of the synthesis that did agree with our nominal specification. We took a look at the acceleration response. And I think in our case, our overall level was about 13.7 GRMS. This one came out just a tad higher, but that's okay. We're not going to worry about that. Okay, here's a formula. I sort of just mentioned this earlier, and this is from we've covered this in a previous unit, but just as a reminder, the RMS squared equals the standard deviation squared plus the mean squared. So in many cases, for the random vibration testing and analysis we do, the mean value is 0. So we kind of get into a little bit of a lazy habit of just using RMS and the 1 sigma value interchangeably. And that's okay as long as we realize, and everyone realizes, that that there's a 0 mean value. Okay, here was the single degree of freedom response to the synthesis, and it had a narrowband histogram. So we have counts versus acceleration in G, where the G values are from the instantaneous acceleration response and put into bins. Now here's what I really wanted to get to. We're going to use a variation of Miner's rule, but it's a little bit different. And this one here, I'm going to tell you right off, this has no absolute meaning. On an absolute basis, this has no meaning whatsoever. This will not predict whether a part will fail or not. This is rather what it is. It's a relative damage comparison metric. And that's what it's good for. It's good for, this formula is good for comparing the effect of 2 different environments on a system. And for our system, it's going to be a single degree of freedom system, but this could be used for multi-degree of freedom systems as well. So A here is going to be the response amplitude from the rainflow analysis. So we're going to do a rainflow analysis based on the peaks, and we're going to sort those peaks into different rainflow cycles. So each rainflow cycle is going to have an amplitude, which we're going to simplify and say that that's a 0 to peak amplitude. More properly, it's peak minus valley, and then that difference divided by 2. Then the corresponding number of cycles. This is going to be a binary number, but when I say binary, it can either be 1/2 or 1. So either 0.5 or unity, because each rainflow cycle is either going to count as a half cycle or a whole cycle. And so what we can do is just take our response time history, run through our rainflow algorithm, and we'll get the A sub I values and the corresponding N sub I, which is the corresponding number of cycles. Now here's where our fatigue exponent enters in. And fatigue exponent is really a big deal. Then we take the summation, that gives us our relative damage. Now why is fatigue exponent such a big deal? Because it's an exponent, and whether we set B equal to 4 or 6.4 or 9 or whatever, that has a huge difference on what this damage is going to be. But for our purposes, we're gonna say that's okay, because when we compare our 2 different environments and run them through this formula, we're going to have the same B value for each of those 2 environments. And if there's any uncertainty whatsoever as to what that B value should be, we might do kind of a family of B values or parametric study or whatever, as long as we're consistent between the 2 different environments. And today, our 2 environments, one's the NAVNET PSD, and then the other is going to be a Sine environment, which we're going to get to shortly. So let's go ahead and this just shows you how to run the rainflow, but I'm going to demonstrate that in class, and then you can go back to the slides at your leisure. Okay, so we've got our acceleration underscore response, and let me just make sure I've saved that. So this is the response of our 300 Hertz, Q is equal to 10, spring mass oscillator. And let's go to rainflow fatigue. And this one, we've talked about it last time or two. Let's go over it again. This is rainflow cycle counting per ASTM E1049-85 in 2005. This is based on the research of Endo and Matsuishi, who were two Japanese engineers back in 1968, wrote a historic paper on rainflow cycle counting. So the input array must have two columns, time in seconds and amplitude. And note that the amplitude, in our case, the way we're defining amplitude is going to be peak minus valley divided by 2. So preloaded into MATLAB, we have Excel_RESP. That's the response of our spring mass system. And it's very important, when we do rainflow, we don't do it on the input. Rather, we do it on the response. Very important. Okay, and this is acceleration in G's. Display table, yes. Figure, no. We're actually not going to do anything with the table or figures, but I like to turn them on anyways, because when I see those tables pop up, then I know my calculation is done. We can either use MATLAB directly, which can be slow, or we can use a MATLAB MEX, which interfaces with a C++ compiled program. And we've talked about this before, but I've got the steps on how to set up your MATLAB with a C++ compiler if you want to do the faster MEX method, and which I encourage you to do. And these steps here, you see a couple steps here. These are one-time only steps that you would do. You should only need to do them once. Okay, let's go ahead and run our rainflow calculation on Excel_RESP. So then we get this bin table. NASA likes these rainflow bin tables, and it's fine with me if they like them. But I say, well, why even bother to bin your data? Let's just take the acceleration and cycles data for each, go cycle by cycle or half cycle by half cycle, and then run that into our Miner's rule, or that the equivalent relative damage variant. Here's a plot. We're just going to ignore that one. This is our acceleration time history. It's actually the response time history for our oscillator. It pops up again, and this is the one where, as we zoom in a couple of times, you can see that, yay, verily, it's a 300 Hertz system, which you could verify by counting the number of peaks and dividing by the corresponding time step. Okay, so in this case, we don't even need to save the amplitude and cycles. We can go directly to calculating the relative damage. So what is the relative damage for 6.4 fatigue exponent? So the relative damage comes out to be 2.406 times 10 to the 13th power. Let's just kind of sort of copy and paste that, because we're going to be using that here shortly, as you'll see. So this is the time domain damage, method. Now, we could have also, as an alternative, we could have calculated the same value by staying strictly within the frequency domain. But we decided to do the time domain method today, even though it's a bit like a Rube Goldberg cartoon, because I wanted you to sort of get an appreciation for the histograms for some reasons that are going to become clear. Maybe at the end of the unit I'll go back and show you how we can also do this, arrive at the same results by staying strictly in the frequency domain. Okay, we'll see how I'm feeling. So what are we going to do next? So we have this damage value. Now this damage value, you wonder, what's the units? It's G raised to the power of 6.4. Now, isn't that kind of crazy? Yes, it is crazy. To a physicist, that's that's nothing. That's garbage. But we're not physicists. We're engineers, and for engineering purposes, this is a valuable metric, and you're going to see why shortly. And we're going to do something that no self-respecting physicist would ever do. Okay, so what's that going to be? Let's go to our slides. And so in this slide here, just as a reminder, I show you how to go ahead and do that rainflow calculation that we just did with all the parameters we selected. It looks like in this slide I was going to save the amplitude and cycles, but we don't necessarily need to do that because we can go directly to the relative damage calculation. Just type in our fatigue exponent, calculate, and we get our damage result. So in this case, it was 2.607 times 10 to the 13th. And in this case, for what I demonstrated in class, it's also 10 to the 13th, but it's 2.04. And the fact that this has a 2.4, whereas if you squint your eyes, this is 2.6, that just doesn't bother us at all, because any minor differences in the way those random numbers were generated for the original base input, any minor difference gets, I'm not going to say multiplied because that's the wrong term, but it gets raised to the power of 6.4. So any subtle differences can get turned into some fairly large differences because this exponent is so high. Okay. Let's see. And I think, as I told you, I think was it last time or the time before, any time we're doing fatigue calculations, this is all ballpark calculations. Here I show, oh yeah, let's go out to the third decimal point. Well, okay. It's kind of silly just to really go beyond the first decimal point. Now, for what we want to do, the whole purpose of this exercise is once we get that damage from our random vibration, we want to come up with an equivalent sine level. And this will be an equivalent sine level where the sinusoidal frequency is at 300 Hertz, which is the natural frequency of our spring mass oscillator. And we're going to be consistent, so we're going to have Q is equal to 10. That's the amplification factor, equivalent to 5% damping. The fatigue exponent, it's important to be consistent here as well, 6.4. And it turns out for doing the rainflow calculation for a sinusoidal response, it's almost trivial. We do not need Endo and Matsuishi's algorithm. We don't need that ASTM spec. It's just really intuitively clear how to calculate the rainflow for a sine input. So, okay, here we have our spring mass system again. Y double dot's the input. Now, this Y here is actually supposed to be Y double dot. So this is going to be our base input acceleration. And again, it's not the input we're concerned about, it's the response. So to get the, of course, to get the response, you need to consider what the input is. But so if we take Q, which is our amplification factor, times our base input acceleration, then this term in parentheses becomes the response of our spring mass system as subjected to the sinusoidal base excitation. So Qy is the response. So we take that response and we raise it to the exponent b, which in our case will be 6.4. Again, Q is equal to 10. And the number of cycles is trivial here. It's very nearly trivial to calculate. We just take the frequency of the oscillator, which is cycles per second, multiply that by duration, that's the number of cycles. And that's all there is to calculating the damage, this relative damage index for steady state sine response. We don't even need a series. It's just a 5 variables, a simple calculation. So we're going to go ahead and do that for our case. And well, let me show you the next slide here. So we take this formula here, and in our case, we know all of these variables except we do not yet know what our Y base input acceleration is. We know what D is because we just calculated that for the random vibration case. And we're trying to come up with a so-called equivalent sine level, which for fatigue. Now, in this unit today, the only thing we're concerned about is fatigue. Now, is fatigue the only failure mode? No, it's not the only possible failure mode. We could, for example, have loss of clearance, loss of sway space, loss of alignment, mechanical interference, and each one of those would be a relative displacement type of a failure mode. And there's others as well. Just some systems will fail if the acceleration reaches a certain peak threshold. Think about maybe like an ultimate stress failure, for example. But we're going to assume that our response levels are at least somewhat below the ultimate stress limit, whatever that might be for a spring mass system, and that our only failure mode of interest is fatigue. And for random vibration, usually it is fatigue that we're concerned about, with some exceptions. So we just take that formula and we just rearrange it so we can solve for y. So just some simple algebra there. So let's go ahead and do this calculation. And as you might well imagine, we have a MATLAB script to do that. It's so easy you could just do that calculation yourself, but it's a hand calculation. But let's go ahead. Now, one of the things I've added for version 6.6 is I've had different fatigue things in different places, and I want to also have a way just to group all the fatigue functions together. So I have fatigue toolbox. Let's go to fatigue toolbox here, and you can see one of our favorites that we covered. Was it 2 weeks ago? I think was Steinberg's circuit board fatigue, and I've moved that. Steinberg's circuit board fatigue used to be directly under miscellaneous, but now it's grouped together in fatigue toolbox. But actually, we're not going to do that one today. But we are going to come back to that later. So let's do equivalent sine input for a given damage level. So let's perform this analysis. So this script calculates the equivalent sine level for a single degree of freedom system subjected to base excitation given a reference damage index. Well, here's our reference damage index. It's the one we calculated for our NAVNET PSD as applied to the spring mass oscillator. So Q is equal to 10, fatigue exponent 6.4. I already have these as the initial values, but you can change those if you like. 300 hertz is going to be our natural frequency, and our duration is 60 seconds. So what is the equivalent pure sine tone at 300 hertz to give us the same amount of damage that the NAVNET base input would provoke? It comes out to be about 2.67 Gs. So 300 hertz, 2.67 Gs is equivalent in the damage it will cause for a spring mass system with Q is equal to 10, natural frequency of 300 hertz, fatigue exponent 6.4, and this duration, I say 60 seconds, but really this duration just has to equal whatever the PSD duration is. So there you are. That's how we can come up with an equivalent sine tone for a PSD. Now, why would we ever want to do that? Well, I'll leave that up to you. I suppose one, at least hypothetically, could substitute the pure sine test for the random test, given this set of assumed parameters. There are also times, maybe when we're doing finite element modeling or other types of tests, where there is a need to convert from sine to random or vice versa. There could be a case, for example, let's just say hypothetically that that spring mass system actually represented our avionics component with these assumed parameters. And let's say we had already done the random vibration test because that was what our specification was. Now, later on in the program, someone comes along and says, well, the specification is supposed to be different. That box does not need to pass that NAVNET spec after all. Rather, it has to pass this sinusoidal test, this pure sine test. Well, to retest a component takes time and money and can cause schedule delays and all that. So is it possible to say that the component is good to go for the new pure sine requirement based on the fact it's already been tested to the NAVNET random vibration? And so we've just shown a way that we could make that comparison within a set of assumptions. Another thing, and I do need to be I do need to be honest and upfront with you here. Is that we do the best we can. We're engineers, we're not physicists. And I've been in meetings with some of my esteemed colleagues who say, and understandably so, that anytime we're doing our analyses, especially like a finite element analysis or whatever, that these Q values or the equivalent damping, that's the biggest uncertainty factor. And to some extent I agree with them, because damping can only be measured. It cannot be predicted ahead of time. So there are some reference databases we can consult for typical damping, but for your own particular component or subsystem, whatever it might be, it's imperative you go out and find out for yourself what the damping value is for your system. And just to throw another little monkey wrench in, damping can be nonlinear depending on the input level. That's just another little thing to be concerned about. So if you want to repeat these analyses, for example, you can do that using different Q values and different fatigue exponents. Just be consistent between the sine and random. And let's see where we're at here. I guess before we go on to our next unit, let's see if we can show you how to get the same damage value from the random only by remaining in the frequency domain. Now the whole reason, in fact, let me go to the slides first. The whole reason I did this roundabout method of doing this time domain synthesis and all that was because I just wanted to emphasize that the histograms for sine and random are different. Now, the histogram on the left represents a bell curve, and we saw that both our input and our response had a bell curve histogram for that, based on that NAVNET PSD. So both input and response had a bell curve histogram. Now, for sine vibration, for both input and response for that oscillator, both of those have a bathtub curve histogram. So if you want to be a purist, you could say there is absolutely no way to make an equivalence between random and sine vibration because they have such different histograms. It's comparing apples to oranges. And as we look at this random, the levels tend to fall near zero, but there is a distribution, and there are some peaks that go out to 3 sigma, even 4.5, 4.6 sigma on either side. Whereas with sine, the levels tend to stay near the peak positive, peak negative values with well-defined limits with a fairly rapid transition in between. So the fact is, random and sine are two very, very different environments. But in the engineering sense, and again, this is engineering, not physics, we can make a comparison between those two in terms of the variation on Miner's rule, where we take the relative fatigue damage and using rainflow as part of that process. Okay, now I do want to show you the random vibration, how we could have gotten the same damage or similar damage in the frequency domain. And let's see, I'm going to put myself on the spot and see if I can do this here. So let's go to power spectral density, SDOF response to base input. We've run this one before, so I'm not going to go through all the details. NAVNET _spec is our PSD base input, English units. It is a specification, so I'll interpolate. 300 hertz. Q is equal to 10, 60 seconds. The maximum plot, okay, this is a 20 to 2000 hertz. There's a side note here that the duration only affects the maximum expected peak. It does not affect the RMS value or the 3 sigma values. Calculate. So here we have in the, and this is really this is the same calculation we did in the time domain, only now we're doing the equivalent in the frequency domain. So we have power spectral density and 300 hertz, Q is equal to 10. The green line is our base input from the NAVNET spec. And this is G squared per hertz versus frequency in hertz. The blue curve is how the spring mass system responds to that base input. So you can see at lower frequencies there's unity gain, and as we approach the 300 Hertz natural frequency there's a tremendous amount of dynamic amplification. And then above a frequency which is equivalent to 300 Hertz times the square root of 2, a filtering effect occurs. So the blue line is what we use for our fatigue calculations because that's the response. Then here's the corresponding power transmissibility curve, which is G square out divided by G square in. Again, 300 Hertz, Q is equal to 10. Now, this is a Q is equal to 10 system. It's a spring mass single degree of freedom system. So the peak transmissibility at resonance is Q squared. But that neat and tidy rule really only works for the case of a spring mass system driven at resonance. If we have a multi-degree of freedom system or a continuous beam like a cantilever beam, this peak would have a different value at the resonant frequency. And sort of the bottom line, the quick story is if this were measured data and we were trying to pick off the Q value, we would not say, okay, let's just go over here, pick off Q squared. Instead, it's much better, more robust and all that to use the half power bandwidth or 3 dB bandwidth method, which we've done before. And I'm not going to repeat that, but we've done that in class before. So for experimental data, please use the half power bandwidth method. Okay, let's go ahead and we're going to save this. We've done the calculation. And this number should look familiar to you. In the frequency domain, the response, the PSD response for oscillator is 13.7 GRMS, and we have that same value in our time domain method. So let's just save this as, I don't know, I'll call it response underscore PSD. And how are we going to calculate the, let me see if I have something here. We've got, I'm just sort of checking a few things here. I need to go in and put another function here, or maybe put, or put it in the fatigue toolbox. But let's go to the, let's actually go to the VRS option, and underneath VRS you see fatigue damage spectrum, but actually both of those choices go the same place. I'll show you what that is. So we've run this before. This is the vibration response spectrum of a single degree of freedom system subjected to a base input power spectral density. And we can also calculate a fatigue damage spectrum. And we're actually going to cover that in more detail, in earnest, in a future webinar. But we'll just kind of do a quick preview, a sneak preview of FDS today. So we type in our NAVNET spec. We're going to go from 20 to 2000 Hertz. English units, Q is equal to 10, 60 seconds long. We're going to calculate both the vibration response spectrum and the FDS, fatigue damage spectrum. We need our fatigue exponent 6.4, and we're going to do that based on the acceleration. Let's go ahead and calculate, see what we get. We'll take a little bit of time here. Bunch of curves go by. Now, you've seen these sorts of curves before because we've already covered vibration response spectrum. Okay, here's our NAVNET PSD base input, G squared per Hertz versus frequency in Hertz. Here's our acceleration vibration response spectrum. So we have acceleration in G versus natural frequency in Hertz. Q is equal to 10 is duly noted. Now this red curve here is the 1 sigma, or you could say it's the RMS value, because we have zero mean. So that comes out to be pretty close to 13.7 Gs, which we already knew from our time domain calculation, and also for that previous single degree of freedom response analysis that, yes, at 300 Hertz natural frequency, we do get a response of 13.7 Gs. So that's just confirming something that we already know, but it's good to double check. We have a relative displacement VRS, and we're not going to really cover that now, but I will say just as you look at, let's just look at the red curve here. For design purposes, if we want to minimize relative displacement, it's best to have a really stiff mounting system. And actually, if we could have perfectly hard mounted system, in other words, stiffness goes to infinity, then relative displacement goes to 0. So if our concern is minimizing relative displacement, a higher natural frequency is to be desired. On the other hand, if we want to minimize our acceleration response, then we want a lower natural frequency. So in other words, we want to isolate our system using a soft spring mount. So what is the right way to go for your system? I don't know, but you have some choices there. What did we, we want to look at the fatigue damage spectrum. That's our new. So this is a new plot, and again, I want to go over this more earnestly in a future webinar. But this is a preview. Acceleration fatigue damage spectrum. Q is equal to 10, 6.4 fatigue exponent. So here we have this really funny unit. It's G raised to the exponent 6.4, same thing as over here. And at 300 hertz, you can see we get 2.21 e to the 13th. Well, that's pretty close, about 10% or so of what we have from our time domain calculation. But we did not do any time domain calculation to generate this curve. This was all done really in the frequency domain. So the point is, and this is something I find quite fascinating, is we're doing our various shock and vibration analyses. We can do things in the time domain or the frequency domain, and it should all come out pretty close to being the same. So just as a reminder, we've now calculated that damage value 2 different ways, and then we've also come up with the equivalent sinusoidal base input at 300 hertz with Q is equal to 10 and B is equal to 6.4. So we're now done with the first half of our unit for today. Now let's go to the second part. And the second part requires we go back to slides. Okay, so now we're going to do somewhat the opposite thing. We're going to convert a sine tone to a narrowband PSD. Well, why would you ever want to do that? Well, you could have a sinusoidal test spec, and for whatever reasons, you prefer to test your item on the shaker table using a narrowband random PSD. Maybe it's easier to control or whatever. There's also a case when people are doing finite element analyses, and they might have a sine on random specification, and in order just to keep things easy for their finite element analysis, they want to take that sine tone, convert that to equivalent narrowband PSD, then superimpose that on the broadband PSD, and then just do their finite element analysis that way. And that's reasonable within a series of assumptions. One thing that's interesting is that when we make our equivalent narrowband PSD for our sine tone, that's going to be a G square per hertz level. And let's say it's really a sine on random specification, so some broadband random. It turns out with PSDs, given G square per hertz, those G square per hertz values can be added directly. So that makes it a quick, really easy to take our narrowband PSD representing the sine and then just superimpose it on our broadband random, if in fact we have a sine on random specification. Okay, so let's see. Again, we're going to base this on the acceleration response of the mass for both sine and random. Again, we're going to have to assume a Q value and fatigue exponent. And we're going to calculate the fatigue damage for the sine tone. Now, once we have that, then we're going to say, okay, let's come up with equivalent narrowband PSD that has that same fatigue damage. So to do that, we're just going to, well, we have to select our frequency limits. In our frequency limits, I'm going to propose we use 1/12 octave band spacing. So the center frequency of that band will be the same as the sine tone frequency. Now we're going to assume an initial PSD level of 1 G square per hertz. So we have a 1/12 octave band PSD centered about the sinusoidal tone frequency with an initial level of 1 G square per hertz. Then we're going to calculate the single degree of freedom response to the narrowband PSD. and then we're going to calculate the equivalent narrowband damage. We could do this using the time domain method, but just to be real quick and simple and easy, we're going to use the derelict method. Now the derelict method is going to give us, in almost all cases, unless we got really lucky, is going to give us a different damage value than did the sinusoidal response analysis. But that's okay, because we can just make a ratio of the two different damage values and rescale this g² per hertz level accordingly. And it turns out this is actually pretty quick and simple to do. And we have as you might imagine, a MATLAB script for doing that. So let's go to vibration data, and let's go to our fatigue toolbox. And down in the bottom right-hand corner, we have equivalent narrowband random PSD for sinusoidal input. Okay, now we've got some parameters, and let me just show you where they are, what they are. We're going to assume that our sine is 100 hertz, pure sine, 18G base input, 60-second duration, fatigue exponent 6.4, Q value equal to 10. So let's just remember those numbers. So let's see how well I did. That's 100 hertz is our sine frequency, base input 18 Gs, 60-second duration, amplification factor Q is equal to 10. What should our g² per hertz value be? It says, look at the command window. Okay. If we look at the command window, we see that, first of all, we see that our fatigue damage index for the sinusoidal response is about 1.6 e to the plus 18th. So in order to come up with an equivalent narrowband PSD that will cause the same acceleration response damage, well, we've already decided it's going to be a 1/12th octave band centered about the 100 hertz sine frequency. And in this case, we will need 15 g² per hertz. So if we have 15 g² per hertz, which is the narrowband level defined between these two frequency limits, that will cause the spring mass oscillator, which we're going to assume is 100 hertz natural frequency, Q is equal to 10, 6.4 fatigue exponent, to have the same damage as would be the case for that pure sine input. Then we also see the overall level there for our narrowband. And I think, let's see, did we have a figure 1, a plot that came up with that? So I think what I might want to do is, maybe not, is I want to go back and add a little plotting routine that will actually show the PSD. But it's just those two breakpoints there. In fact, we'll just call this NPSD for narrowband PSD. Save. And if we go to vibration data, and let's see if this will work. If we go to PSD input, overall RMS, we've run this one before. I'm going to plot from 20 to 2000, even though this is a narrow band, but this will help show you how it's a narrow band. Oh, I put in the fatigue damage there. I don't want the fatigue damage. I want NPSD. You should have caught me on that one. Okay, and we'll ignore all the plots except the acceleration PSD. And where did that go? So what I need to do here is, first of all, let's close out all the other plots. So let's do close all. That'll get rid of all the other plots. Let me replot this. Calculate. Let's get rid of figure 4. Okay, okay, here it is. Here, this is the figure we want. This is our 9.31 GRMS, and just see that little blue line there. That's going to be our narrowband PSD. G² per hertz versus frequency in hertz. And really what I ought to do is maybe have some show an initial ramp and a final ramp, which would be almost infinite slope. But you get the idea. That's just our narrowband PSD. Okay. Now we're going to have to get pretty honest here, and I love these tools, but neither do I want to oversell them. So what I did is I just took that previous script that we just ran for converting a sine tone to a so-called equivalent narrowband PSD. And I said, what would happen if I varied some of these parameters? So for the Q values, I said, okay, Q can either be 10 or it could be 30. And again, this is for an 18G 100 Hertz sine tone converted to a 1/12th octave band PSD, where the center frequency of that band is 100 Hertz. And then for each of the two Q cases, I had B is equal to 4, 6.4, and 9. So I've got 6 permutations. And you can see that amongst those 6 permutations, that G square per Hertz level is going to vary. And as it turned out, whoops, didn't want to do that. Okay, I'm getting a little fat-fingered there. Okay, where that arrow cursor is pointing, that is the worst case PSD going from sine tone to narrowband. And that corresponds to the highest Q and to the lowest B. So if you're uncertain what Q should be and you're uncertain what B should be, then crank up Q a little bit higher and crank down B a little bit lower. And I do have some information on my blog about fatigue exponents, and again, as I mentioned, or as I started to mention, Q, according to my colleagues, is the biggest uncertainty factor, but in fatigue analysis, the effect of B is even a greater uncertainty factor, because that takes our amplitudes and raises them to an exponent. And I do have on my blog, let's see if we can go to vibration data blog, I do have a little bit of information on fatigue exponents, but I have an action item to myself to provide you some further information. Now, the good thing about this relative damage calculations we were doing, we did not need to know the whole SN curve. All we needed to know was the slope. And I just have a little bit of information here I want to add to this. Steel with a welded joint can have a slope of 3 to 3.5. Steinberg's text recommends 6.4 for electronic components. For bare aluminum, we could have maybe 9 or 10. And of course, the slope can be affected by all sorts of factors: stress concentration, notches, mean stress, residual stress, surface roughness, temperature, corrosion, etc., which is all a roundabout way of saying that these are just ballpark calculations. But anyways, you do have some tools here that are good for engineering purposes. And there are certainly times when we're in situations where we have schedules to meet, we have deadlines, we've got to get some result done because we have constraints on cost, on time. And these are the sorts of engineering things that we need to do to get ourselves through so our hardware can get shipped. And we do, most of us anyways, belong to, I know some of you work for NASA, but others of you work with companies where you do have to sell things and make a profit. So at some point, we just have to use our engineering judgment. And I would argue that no matter what we do in engineering, it all comes down, the bottom line is ultimately engineering judgment. That's the bottom line of everything we can do. All these formulas are great, these techniques are great, these methodologies are wonderful, but at the end of the day, it all comes down to engineering judgment. So thanks for participating in this webinar, and hope to see you soon. We've got more rainflow fatigue topics to go. So goodbye for now.